Okay, welcome back. Hope you've had a little bit of fun practicing your tangent and normal and binormal vectors. They're tough. Okay, well, the next thing we're going to do is, well, unfortunately, not much easier. Um, we're now going to talk about acceleration. And unfortunately, acceleration is not as easy as it was before, where it's just simply the second derivative. If only life were so nice. Um, we're going to talk today about tangential and normal acceleration. You have two different types of acceleration acting on an object. Okay, so acceleration, excuse me, acceleration has two components: a tangential component that acts in the line of motion, so it acts in the direction that you're heading, and there's also a normal component that acts perpendicularly to this. Um, we are always going to denote acceleration by the vector a, just like we would if we were working in single variable calculus again, where we would just call it, I guess, not boldface. A wouldn't be a vector, but here it's a vector a. And the first thing that we're going to do here is we're going to prove that it has to lie in the plane determined by your vectors t and n, where t, I'll remind you, is your unit your unit tangent vector, and n is your principal unit normal vector, which is perpendicular or orthogonal to t. Okay, so you'll remember that the formula for t is that it is the derivative of r, which is your position function essentially, divided by the magnitude of r. The magnitude of r prime, sorry. So it's r prime over the magnitude of r prime. It's a unit vector because it's divided by its magnitude, and this is all well and good. So instead of r prime, I'm just going to call it v for your velocity vector. Your velocity vector is given by the derivative of your position vector, so it's just r prime. Okay, so if I rearrange this, just multiply both sides by the magnitude of v, you'll see that you get that v, your velocity vector, is equal to t, your unit tangent normal, multiplied by the magnitude of your vector v. How is this going to be helpful? Well, now we can take the derivative of that to figure out what a is. And so a, again, the acceleration vector, is, if I use the product rule here properly, is going to be the derivative of t, so t prime, times the magnitude of v, plus t times the derivative with respect to time, or whatever your variable t stands for here, of your magnitude, the magnitude of v. So this is just a product rule that's happening here. The prime always means derivative with respect to t. Okay, so again, I've just rewritten what we just discovered here, that a is given by this kind of messy looking formula. And now here comes the magic. What I'm going to do is I'm going to multiply this first term by 1, which is a very tricky move that we do in math a lot. We multiply and divide by the same thing, or we add and subtract the same thing. And so here I'm multiplying by the magnitude of t prime divided by the magnitude of t prime. Again, assuming that that's, yeah, I'm assuming that that's not 0. Okay, why would I do such a thing? Well, because now I can rearrange this first term, and I can put the numerator outside, and I can put the t prime inside. And the reason for doing this is because t prime divided by the magnitude of t prime is the normal vector, the principal unit normal vector, n. And so by doing this, you'll see that I left the right side of this, the right term here alone every step along the way. By doing this, what I've got is that a, the acceleration, is going to be equal to the norm of t prime times the norm of v multiplied by our vector n, plus our vector t times the derivative with respect to time of v. This is all very awful looking, but the point is that what we're getting is a linear combination of the vectors n and t, which is very nice, because that implies that if you take a linear combination of two vectors, that vector that you're getting must be in the same plane. And that's what we're trying to prove here, that our acceleration vector is in the same plane as the one determined by the two vectors n and t. Okay, perfect. So again, here just copying the horrible formula down again. This gives us our two different components. So the component that we're multiplying by the unit tangent vector, here it's the derivative d by dt of the magnitude of v. That's called the tangential component of acceleration, because it's acting in the same direction as the tangent vector is going. And the coefficient of n here, which is the magnitude of t prime times the magnitude of v. And again, these could all depend on time, right? These are not just constants. They could depend on time. But that coefficient, that expression that we're multiplying by n, that is what we call the normal component of acceleration, which also has another name that any of you taking physics out there might know it as the centripetal component of acceleration. And this has to do with centripetal force. Okay. What do we have next? Here's the notation that we're going to use. Again, a is your acceleration vector. It oftentimes is going to depend on t, so it's going to be a function of some parameter t, and it's given by a sub t, and that's a vector t, that subscript, times t of t plus a sub n, and again that's a vector n times n of t. And again, a sub t is given by this derivative of the magnitude of v, and the a sub n is given by the magnitude of t prime times the magnitude of v. And those are your components of your acceleration. Okay. Those formulas are hard to deal with sometimes, and so there is an easier way, and you're going to prove these in your homework this week, in your problem set. So again, my first component here, a sub t, my tangential component, is given by this kind of ugly formula of t times the derivative with respect to time of the magnitude of v. But what one can show, and what you will show in your homework, is that this is the same thing as the dot product of t and a, your acceleration vector, which is kind of nice. Which furthermore, because t is just v over the magnitude of v, this is given by the velocity vector dotted with the acceleration vector divided by the magnitude of v. And that's the formula that we're going to use. That's the easy one of the an easier way to deal with this. Again, you'll be proving this in your homework this week, but we're going to use the result right now. Here's the formula for the other component, the normal component, or the centripetal component of acceleration. So again, the horrible formula gives us that it's the magnitude of t prime times the magnitude of v. But what you're going to show in your homework is that this is the same thing as the normal vector, the principal unit normal vector, dotted with the acceleration, which is very exciting. So we could use that formula. This happens to also be equal to the magnitude of the cross product of v and a. Since we're taking a magnitude, it doesn't matter what order we do this in, but typically we write v cross a instead of a cross v, and then we're dividing by the magnitude of the norm of v. That's the formula we're going to use. What you'll also see in your homework is, and sometimes this formula is useful as well, is that this is further equal to this kind of interesting looking square root. So you'll be proving that all these things are equal in your homework this week, but we're going to use it now. The key ones being, let's see, we're going to use, I guess, this one and this one. Okay, perfect. So, let's do an example. Let's find the tangential and the normal components of acceleration for this position vector, 3t, negative t, t squared. So if you want to pause here and try this out yourselves, go right ahead. We're going to move on ahead, though, without you. Welcome back. V, the derivative of this, v, so velocity is given by, of course, 3, negative 1, 2t. Piece of cake. The magnitude of that, just square all the components, add them together, and you'll see that you get the square root of 10 plus 4t squared. Not too bad so far. My acceleration vector, very easy to calculate, it's just the derivative of v, so it's going to be 0, 0, 2. And v cross a. This cross product actually isn't too hard to do by hand because there's a lot of nice zeros in the a vector. But feel free to use a calculator or something if you need it. What you'll see is that the cross product here is negative 2, negative 6, 0. So what is my tangential component of acceleration? Remember the shortcut, the sweet formula that we have, which you're proving, is that it's v dot a over the magnitude of v. And here you can see if you take the dot product of v and a, because of those handy zeros again, we really only have the z components multiplied together, which is 4t. And we're dividing by the magnitude of v, which is already simplified for us. And so there you go. There's your, at any time t, we can talk about and how we're accelerating along the curve, I guess, in the direction that this object is moving. And for the normal component, the centripetal component, this is again given by the magnitude of v cross a over the magnitude of v. V cross a, again, we calculated was negative 2, negative 6, 0. Take the magnitude of that vector and you get 2 root 10, or you can just leave it as root 40 if you want. Don't worry about cleaning up radicals in this class. The magnitude of v is the same as it was before, root 10 plus 4t squared. And so there you go. That gives you your two components of acceleration. You'll be doing a few of these again this week, just to kind of practice. Again, we're going to see the utility of this later, but for now it is just kind of an exercise and a review of calculus rules that you know and love. Okay, good luck, have fun. See you all later.